Okay, welcome to the next one, which is about the conservation of energy and momentum. And we look at things called closed systems. So in a closed system, the energy is contained, but may be degraded to lower forms such as heat and sound. So even though we have a closed energy system, the energy is not always recoverable because it could disappear down to a lower level and be impossible to get back. Now, some of this is a revision of last year. In fact, most of it will be, because we remember, of course, momentum equals mv, and kilogram metre sector minus 1, which you can get from the equation. In all of our collisions, momentum is conserved. Right, that's the technical term that people use, but we need to understand what that means. And that means momentum before equals momentum after. That's all it means. Like, that's what conservation of momentum means. So let's do an example. So we're always using carts in physics. They're very common. So we've got a 3 kilogram cart at rest, got a 2 kilogram cart going at 8 ms to minus 1. They collide, and afterwards they don't always stick together, but there are often sticky together questions. They stick together, so you've got the 2 kilogram, you've got the 3 kilogram, and they're going at V3. And the question, of course, then is, how do we calculate the momentum? Because there are two masses, m1 v1 plus m2 v2 equals m1 v3 plus m2 v4, and that's a very general statement that applies in all situations where you have the two masses. So that applies to all, but when they stick, we can do m1 v1 plus m2 v2 equals m1 plus m2 v3, because they stick together, so there's a combined mass. That's just fine to put in the numbers. So 2 by 8 plus 3 times 0 equals 2 plus 3 v3, which brings us down to 16 equals 5 v3, or v3 equals 3.2 meters per second. And because the km is positive, it means it goes to the right. Sorry, forgot to move the camera. Well, I shouldn't say it means it goes to the right, it means it goes the original direction, because we define that as positive. Let's do another example. So, example 2. Same 2 carts as before. 2 kilograms, 3 kilograms, and afterwards 2 kilograms, 3 kilograms. Now let's put some rules in. And the second one is at rest. The third one has an unknown velocity v3, and the 3 kilogram this time is going off at 6 ms to minus 1. And the question of course is, what happens? Let's do it all again. So, putting in the numbers, equals 2 by v3 plus 3 by 6. So if you work all that out, 16 equals 2 v3 plus 18, and if you rearrange it, 2v3 equals minus 2, so that v3 equals minus 1. It means it's going backwards. Let's look at energy. Energy is constant, but can be transformed. So, even though it's constant, it can be transformed. Right, let's look at a kinetic energy example. Okay, in our kinetic energy example, there's a very typical example. A cart is on top, we're making ours 5 kilograms. The vertical height change is going to be 10 meters, but the cart is already going at 2 ms to minus 1, and the track is smooth, which of course is physics 4. There is no friction. So normally we label points like A and B, and the whole point of this is we're trying to find the speed at B. Let's try the speed at B. So what's the speed at B? And we know that the speed at B, the cart has the EK from the top, so the kinetic from A plus the gravitational potential that it gains. So What that therefore means, once you understand the whole thing, is that at the bottom we can just simply go straight into the half mv squared version, because we know that the total energy is going to be the same. So total energy at top and bottom is the same. So therefore, EK at B equals EK at A plus the energy that's gained. So a half mv squared at B equals a half mv squared at A plus mgh. So we put all those together, 0.5 by 5 by velocity b squared, 0.5 by 5 by 2 squared, plus 5 by 9.8 by 10, and it all works out to be 2.5 VB squared equals 500 joules, so that VB turns out to be 14.1 ms to minus 1. This is a very, sorry I cut the bottom off, I'll put that back on the screen and leave that there for a minute. What this means is that we can do lots and lots of energy interchange questions and versions, because we can use it with projectiles, we can use it with falling bodies or bodies that are shot straight up, and we can use energy to supplement the fact that we can do it with kinematics, and they interchange with each other. Okay, and this one is for Monday, but we'll also do this one on Wednesday.